If I walked up to you and told you that I had weighed the Earth, not just a piece of the Earth, but the whole thing, oceans, continents, mountains, everything, by measuring the force of 1/3 of a grain of salt, would you believe me? Or would you laugh and call me crazy? In 18th century England, an English natural philosopher named Henry Cavendish declared that he had done just that. To present day, the methods he used and the values he derived are still regarded as foundational to the physics of the heliocentric model. His most renowned work, simply referred to as the Cavendish experiments, is still frequently cited as experimental evidence of the validity of Newtonian gravity and gravitation. Who was he? What did he do? And is his work valid and useful for our understanding the world around us today? In order to understand Cavendish's work, we need to go back to the 17th century and discuss the works of mathematician, physicist, astronomer, theologian, and the world's most prolific occult author, Sir Isaac Newton. Newton, whose occult interests included alchemy, sacred geometry, biblical end times prophecy, and chronology, was determined that the motion of the heavenly bodies was motivated by invisible spiritual forces, and not merely physical ones. In 1687, he published his 3-volume treatise on classical physics titled Philosophiae Naturalis Principia Mathematica, Principia for short, or the Mathematical Principles of Natural Philosophy. In it, he described his laws of motion, which, among other things, described the observable behavior and properties of physical matter on Earth. Newton's second law states, the alteration of motion is ever proportional to the motive force impressed, and is made in the direction of the right line in which that force is impressed, and defined force as a product of mass and acceleration with his famous equation, F equals ma. Newton's equation had fundamental implications for how the world is viewed. An object's weight was no longer a physical attribute of the object, but rather an effect caused by acceleration. Mass was defined as the amount of matter present in an object. It is the acceleration of this matter or mass that produces a force, or what we call weight. The equation can be rewritten as weight equals mass times acceleration. Since assigning a zero value for acceleration results in zero force or weight, an object at rest is defined as experiencing an acceleration. Newton attributed this acceleration to gravity. Hence, it is gravity that gives an object its weight, not the physical properties of the object alone. But what is gravity? Today, as it was then, the effects that Newton defined in his F equals ma can be observed, measured, and empirically studied everywhere on Earth. What he described mathematically is what we experience as the weight of an object. The acceleration Newton described is defined in physics as little g, or Earth-specific gravity. Ignoring the effects of air resistance, a free-falling object will accelerate at approximately 9.81 meters per second every second in Earth's atmosphere near sea level. Newton went further. In his universal law of gravitation, he asserted that Earth's little g was the local effects of a universal force called gravitation. Gravitation, or big G, was defined as a universal and constant attractive force existing between all masses. He hypothesized that it applied as much to the behaviors of the celestial objects as it applied to objects on Earth. His equation to describe the law of gravitation, F equals big G times mass 1 times mass 2 over distance squared, held that the gravitational force between masses is a product of the two masses divided by the square of the distance between their center points, multiplied by big G, his hypothesized constant. Let's walk through an example of how we would apply Newton's law to an object on Earth. Since F, force, is the empirically measured acceleration on Earth's surface of 9.81 meters per second squared times the mass of our object, we can rewrite the equation as ma equals g times mass 1 times mass 2 over distance squared. In our example, mass 1 is the mass of an object on Earth. Mass 2 is the mass of the Earth itself. Let's solve for the acceleration of our object, m1. Since we have our mass on both sides of the equation, we can cross-cancel to get acceleration equals big G times the mass of the Earth divided by distance squared. Notice that we are now solving for acceleration, which is little g in our example. If we describe our equation in words, acceleration on Earth for our object, little g, is due to the gravitational constant times the mass of the Earth divided by the distance between the centers of the masses squared. In this case, the distance between the masses is measured from the Earth's center point to the center point of our object. Hence, it is not the object that has weight or falls, it is the force of gravitation caused by the mutual attraction between the mass of the Earth and the mass of our object that attracts it to its center, giving it what we experience as the object's weight. In summary, F equals ma stated that weight is a force caused by gravity, not an inherent trait of matter. An object's weight and the reason it falls to the Earth is due to the mutual attraction between its mass and the mass of the Earth. An object at rest is undergoing an acceleration. The law of gravitation was hypothesized to apply to any two masses, including the Sun and the Earth, any of the celestial bodies, and any two items on the Earth's surface. In this way, Newton attributed the falling of the apple from the tree to the same force that ordered the heavens. Newton's F equal ma and the inclusion of big G, the gravitational constant, in Newton's equation for universal gravitation marks a transformative point in physics, as it is the union between the observable and measurable traits of matter on Earth with the philosophy and dogma of heliocentrism. With F equals ma, Newton defined weight and force as effects of gravity. By including the constant in his theory of gravitation, he tied the fundamental attributes and behaviors of matter he had defined in F equals ma to his cosmology. Thus, the empirical and observable behaviors of reality were conjoined with a theoretical and unmeasurable force central to heliocentrism. It is an event that physicists have referred to as the first great unification. It is the globe model's first miracle, and the reason for Newton's and later Cavendish's deifications. Quite different from his laws of motion, which were based solely on observable, repeatable experimentation and deductive reasoning. Newton's law of gravitation was the product of inductive reasoning, in which he extrapolated his empirical first-person study of natural phenomena and applied it to the heliocentric world he envisioned. Deductive reasoning is the form of logic that forms the basis for the classic scientific method, whereby one works from theory and hypothesis to observation and confirmation via experimentation. Conversely, inductive reasoning uses specific observations to identify patterns and build a hypothesis and theory from them. In other words, the end result of deductive reasoning is empirical data, while the end result of inductive reasoning are theories and hypotheses. Deduction leads to data and information. Induction leads to speculation and supposition. Newton himself seemed to caution against the use of inductive reasoning. His Principia includes a number of famous dictums for experimental philosophy, including one referred to as hypotheses non fingo, or I feign no hypothesis. Newton seems to acknowledge his use of both forms of reasoning while at the same time insisting that deduction was appropriate for experimental philosophy and cautioning against the use of inductive reasoning. Here is a modern translation. Hitherto we have explained the phenomenon of the heavens and of our sea by the power of gravity, but have not yet assigned the cause of this power. I have not been able to discover the cause of these properties of gravity from phenomena, and I frame no hypotheses. For whatever is not deduced from the phenomena is to be called a hypothesis, and hypotheses, whether metaphysical or physical, whether of occult qualities or mechanical, have no place in experimental philosophy. To us, it is enough that gravity does really exist, and acts according to the laws which we have explained, and abundantly serves to account for all the motions of the celestial bodies and of our sea. So on the one hand, Newton cautions us about drawing any conclusions aside from those that can be deduced via experimentation, while on the other hand insisting that his own inductive hypotheses about the nature of the celestial bodies are wholly natural and justified conclusions. In the years that followed the publication of Principia by the Royal Society of London, Newton's peers and successors were left with the duality of his words. The biggest name in science had given them a masterpiece that supported their heliocentric cosmology, but had stopped short of declaring his gravitational equations empirical. Newton neither gave big G the gravitational constant of value, nor did he name a cause for gravitation. Enter Henry Cavendish. Cavendish conducted his famous experiments more than 100 years after the publication of Newton's Principia and 71 years after Newton's death. A fellow member of Newton's Royal Society, his results were published in 1798 in the Philosophical Transactions of the Royal Society of London, the Society's official publication. He took as inputs Newton's laws of motion and the theory of gravitation, and set out to measure the density of the Earth. Cavendish inherited the idea and the apparatus for his experiment from the late John Michell, who had built it but never had the opportunity to conduct it himself before his passing. For those of you that are new to the subject, I'll briefly describe Cavendish's setup and methods. His apparatus was housed in a small brick building, often referred to as a shed. The masses or balls were located on the interior, equidistant from each wall, and hung from a wooden beam, in the case of the large masses, and a wooden post in the case of the torsion balance with the small masses. The torsion balance was hung from the post and housed in a wooden case. The purpose of the torsion balance was to nullify the effects of gravity and allow the small balls to move freely under the smallest of forces. The balls themselves were attached to a wooden beam that hung from a wire. The wire itself was key to the apparatus since the rotation of the wire is central to the movement of the torsion balance and the small balls. Small masses, made of lead, were housed in a case and hung from the torsion wire and wooden beam. Each one was approximately 3/4 kilogram or 1.61 pounds. The large masses, also made of lead, were hung from a wooden beam and weighed approximately 158 kilograms or 348 pounds. The beam suspending the large masses separated them at roughly the same distance apart as the small balls were hung and was attached to a pulley system that allowed Cavendish to move them closer and further from the small masses. Cavendish observed the apparatus through the brick walls via telescopes that were aligned with the small balls. From this top-down view, we can see the alignment of the small and large masses. All movement of the masses is along a circle of the same circumference. Cavendish's basic method was to move the balls from a middle position somewhere around the M in the diagram to a close proximity to the small balls and then observe the subsequent movement and vibrations of the small balls and torsion balance that resulted. He recorded the movements when the large masses were in mid-position as a control and again when he moved them both to and from the small balls. In other words, he would observe the pre-existing vibrations and movements of the small masses, and then move the large masses with his pulley from position M to next to the small balls, as they are shown in the diagram, and then back again to position M. In summary, Cavendish compiled his results, took the value for the force he had measured, and plugged them into Newton's equations in order to calculate a value for the density of the Earth. An important distinction deserves emphasis. Cavendish did not set out to experimentally establish that mass attracts mass, or that gravity as Newton described it exists. Cavendish's stated purpose was to determine the density of the Earth by measuring the force required to draw the arm aside through a given space. Cavendish had already assumed that mass attracts mass, accepted Newton's theory of gravitation as true, and set out to measure this supposed force with the intent of determining how dense the Earth is. In other words, he had already assumed that the force of gravitation was responsible for little g, and that this force was present in all masses everywhere. Making assumptions without verifying them experimentally goes against the very motto of the Royal Society, the organization that published both Newton and Cavendish. Its motto is nullius in verba, and means take nobody's word for it. The spirit of the motto is anti-authority, declaring the group's intention to take nothing for granted and to verify all facts via experimentation. It's unclear when or if Cavendish's assumptions were verified via experimentation, or whether perhaps the Society's philosophy had changed since its early days. In strict terms, what Cavendish did can be more aptly described as a scientific measurement, not an experiment. The only experimentation Cavendish conducted was to manipulate the variables and condition that he hypothesized might contribute to the error of his measurement, including the material used, the elasticity of the suspension wire, magnetism, and the temperature differential between the large and small balls. In the end, the vibrations that Cavendish measured were never fully explained by any of these variables, a fact he interpreted as meaning that he could safely eliminate or at least calculate the amount of error owing to each. He included that he had successfully measured the force that he set out to measure and proceeded to apply his findings towards his end goal of calculating the density of the Earth. A couple interesting points to highlight. First, Cavendish found that the temperature differential caused such an effect on the movements or vibrations that he referred to this as a defect of the case and stated his intention to rectify it in future experiments. Second, and most importantly, his experiments had nothing to do with establishing that there was a force that acted between masses or discovering the cause of this force. Cavendish did not establish experimentally that mass attracts mass, since gravitation was an assumption and not a variable he manipulated in his experiment. Since Cavendish's time, his measurement has been repeated countless times in a variety of different ways by scientists and others around the world. The internet is littered with videos of everyone from high school students to professors to scientists attempting their own Cavendish measurement with differing success and results. Similar experiments to Cavendish, such as the ones pictured, have been conducted in the lab by physicists using varying materials and measurement techniques, but the fundamental assumptions are largely unchanged. The published results have been fairly consistent with those that Cavendish published, and the current value for big G has changed little from the value derived from his work.
There is an attraction of gravity between the lead balls.
If you take a look at the different samples from amateurs conducting the measurements, you get a decent cross-section of the material, setup, and results achieved outside the lab. Indeed, some of these can hardly be called scientific, while others are just demonstrations. The most careful among them, conducted by a YouTuber named BM Furball, isolated nearly all of the same sources of potential error as Cavendish did, and maybe more. His careful and repeated measurements resulted in the detection of a rotation of the torsion bar of only 0.110 degrees. In the lab, the magnitude of the force has historically been very small. The movement of the weights Cavendish observed equated to about 3/4 of an inch at most. From a micro perspective, 3/4 of an inch is an enormous amount. On a macro scale, and for something that is said to be the glue that holds everything together and responsible for the formation and machinations of everything, the evidence produced is barely a trace amount. But did they measure what they assumed to measure? As even Cavendish described it, the setup is notoriously sensitive to any and all outside forces, including temperature changes, vibrations, wind, building vibrations, and pretty much anything else that could introduce a force of any kind into the environment. And the reason for the sensitivity is pretty simple. The force Cavendish measured is almost unimaginably small, making the margin of error in the experiment very slim. So slim that it is open to interpretation that what Cavendish actually measured was nothing, or as close to it as you can get, or that all of the supposed force that Cavendish measured can be attributed to the error modes inherent in his elaborate and sensitive setup. For the sake of argument, let's take these results on face value. Exactly how small is the force that is measured in terms that we can comprehend and understand? According to Cavendish, the twisting force involved in twisting the torsion balance was 1.74 times 10 to the negative 7 newtons, or 1/50 millionth of the weight of the small ball. That's a tiny force, just a fraction of 1 newton of force. Anything that is 1/50 millionth of anything you can hold in your hand is tiny. But exactly how small is that in terms we can understand? A newton, which is defined as the force required to accelerate 1 kilogram of mass at the rate of 1 meter per second squared, equals in weight to about 3.6 ounces or 102 grams. It is about the same weight as a small apple. Cavendish's force expressed in weight is an equally tiny number and difficult to imagine, regardless of which unit you choose. Unable to think of a way to slice an apple into 50 million pieces, I decided to search for an item with an equivalent weight. My first thought was a drop of water, but it turned out that a raindrop is more than 11,000 times as heavy. How about a grain of rice? Nope. They're around 1,600 times as heavy, still way too big. A grain of sand is about 250 times as heavy. A sesame seed 200 times as heavy. A grain of sugar is 35 times as heavy, getting closer. Poppy seed is 17 times as heavy. And finally, a grain of salt is only about 3 times as heavy. I think in terms of household items, that is about as close as we're going to get. I can't think of anything smaller. So the force we're talking about is equivalent to 1/3 of a grain of salt. But this is an attractive force we're talking about. So what about in terms of something like a magnet? Well, it turns out that the force Cavendish measured is about 1 trillion times weaker than that of a souvenir refrigerator magnet. That's not even big enough to hold a housefly's report card on the fridge, let alone your kid's school picture. It was with the measurement of this force, equivalent to 1/3 of a grain of salt, or 1,000,000,000,000,000,000 times weaker than a fridge magnet, that Cavendish claimed to know the density of the Earth. We'll discuss that more later, including the structures built upon it. But first, let's take a look at the suppositions required to bridge Newton's F equals ma and the law of gravitation that led Cavendish to believe that he could measure the Earth's density. As we've discussed, Cavendish accepted Newton's assertion that objects fall to the Earth because their mass is attracted to the mass of the Earth, that the effects we see are due to the force of gravity. In order to believe this is true, one has to accept that the phenomena of things falling to Earth is self-evident proof of mass attracting mass. Cavendish's whole setup is based on this assumption. After all, the torsion balance is meant to negate the effects of Earth's mass on the small balls in order to isolate the force of gravitation between the large and small balls so that it can be measured. But outside of this experiment, where do we see this relationship on Earth? Besides a few contested experiments about the attraction of plumb bobs to mountains and other similarly esoteric examples, no one on Earth observes mass attracting mass in the way Cavendish measured it. Boulders do not stick to the side of mountains, cars going down the freeway are not pulled towards big rigs hauling steel, and we cannot stick objects to the sides of other objects and have them stay in place by no force other than their own mass. That is simply not a property of matter that we experience in our day-to-day lives. If we go beyond our accessible environment and look to the stars in order to substantiate this assumption, we enter a loop of circular reasoning. Do we know that gravitation must cause gravity on Earth because of our observation of the stars? Or do we know that the stars behave the way they do because of our observations on Earth? Neither have been supported via experimentation. In order to assert them both, at least one of them needs to be more than theoretical. Speaking of the stars, how applicable to the celestial bodies are the forces measured by Cavendish and the other derivative experiments? In other words, how well do they support the case for gravitation? Let's look at the relationship of the Earth to the Sun as an example and apply his results to it to get a feeling for how the force he measured would scale up to the planetary level. Perhaps we can find justification for his assumptions there. The ratios on screen are the figures for the heliocentric model, some of which rely on derivative values from the Cavendish experiment. According to the mathematical model built using the assumptions and values from Newton, Cavendish, and others, the Sun is approximately 150 million kilometers away. The Sun is said to be 1.99 times 10 to the 30 kilogram in mass, while the Earth is said to be 5.97 times 10 to the 24th, or approximately 330,000 times less than the Sun. The radius, diameter, and circumference of the Sun are all 109 times that of the Earth. The Sun has approximately 1.3 million times the volume of the Earth, but is nearly 4 times less dense as the Earth, with each cubic centimeter said to be 1.41 grams per cubic centimeter, while the Earth is approximately 5.5 grams per cubic centimeter. Density and mass are, of course, directly related to our discussion of Cavendish, as the assumed values were derived from the results of his experiments. They are the missing piece of the puzzle that allowed Cavendish's successors to calculate the gravitational constant from his work and extrapolate those values out for the other heavenly bodies. For most people, it's difficult to grasp these values in a way that is meaningful to how we experience the world. The numbers are so large that they might as well be abstract concepts. In an effort to make it more meaningful, I scaled the Sun and Earth down to the size of household objects: a bowling ball for the Sun and a small pebble-sized piece of clay for the Earth. You can see from the table that all ratios were held constant, including distance, which I based on the diameter of the Sun. In my scaled down version, the mass of the Sun is approximately 7.65 kilograms or 17 pounds, with a diameter of 21.8 centimeters or 8.58 inches, while the Earth becomes a 2 millimeter or 1/16 inch, 23 milligram pebble. The distance between the two is 23.5 meters or 77 feet. I then set these up in my backyard at the appropriate distance and tried to visualize how the force of gravitation would work between the two. The same force that acted on Cavendish's balls must be present on this scale for the law of gravitation to hold true. Were we to isolate these two items from all other forces, we should be able to detect this force. Standing in my backyard, it's difficult to imagine that this is possible. Before we look further into the details of this comparison, it's necessary to understand how the law of gravitation was hypothesized to scale. The value for big G, Newton's hypothesized gravitational constant that was derived from Cavendish's reported values, is currently set at 6.674 times 10 to the negative 11 newtons per meter squared per kilogram squared. It is defined as the amount of force or gravitation that two 1 kilogram objects would exert on one another at a distance of 1 meter. Newton defined this force as a constant, an assertion that Cavendish reinforced within the publication of his results with the following excerpt from his 1798 paper. Another objection, perhaps, may be made to these experiments, namely that it is uncertain whether, in these small distances, the force of gravity follows exactly the same law as in greater distances. There is no reason, however, to think that any irregularity of this kind takes place. The force is said to scale with both mass and distance and is impacted by changes in variables in the following ways. Increase or decrease in either mass results in a corresponding linear increase or decrease in the calculated force. An increase in distance results in an exponential decrease in calculated force, while a decrease in distance results in an exponential increase in the calculated force. Doubling of either mass results in double the force, while halving of either mass results in half the calculated force. Doubling of the distance reduces the calculated force to 1/4 of its previous value. Halving the distance quadruples the calculated force. Magnitude increase or decrease of either of the masses results in a corresponding magnitude increase or decrease in the calculated force. And a magnitude increase in distance results in a 2 magnitude decrease in the calculated force, while a magnitude decrease in distance results in a 2 magnitude increase in the calculated force. This type of relationship between the variables is referred to as an inverse square law and is applied to similar calculations such as the force of attraction or repulsion between charged particles, the intensity of light, acoustics, and more. The inverse square law is, of course, part of the theoretical framework published by Newton in Principia. Just like the law of gravitation itself, this inverse relationship is a hypothesis, as Newton had no way to validate these relationships, evidenced by the fact that the gravitational constant itself wasn't determined until long after his death. Another criticism of the equation itself is that multiplying masses is abstraction. How does one multiply a planet by another planet, or a star by a planet, and why would the force of attraction between them depend on this multiplication? If I have one large object and one small object, why is the size of the force imposed on the large object the same as the force imposed on the small object? Why are we increasing the force experienced by one body in accordance with its own size? Perhaps this is why these calculations never moved beyond the theoretical and have offered very little practical value. I bring these up only to point out the abstract nature with which mathematics have already taken us in Newton and Cavendish's time, and will leave deeper investigation of these questions for others. Now that we have a better understanding of how the law of gravitation functions, let's finish the analysis of our scaled-down Sun and Earth. First, how do the ratio of the distances and sizes of our scaled-down Sun and Earth compare to the sizes and distances that Cavendish used in his experiment? Here are the raw measurements for both the scaled-down Sun and Earth and the actual values from the Cavendish experiment. Here are those values translated into ratios between the two. Notice that the big mass in Cavendish was more than 20 times larger than our bowling ball Earth. The small mass was more than 31,000 times bigger than our mini-Earth. And the distance between the masses in the Cavendish experiment is more than 100 times shorter than the distance between bowling ball Sun and pebble Earth. Based on what we know about how the law of gravitation functions, we should expect the force between the latter to be much smaller than that in the Cavendish experiment. Indeed, that is what we see. The calculated force between our mini-Sun and Earth is nearly 7 billion times smaller than the force Cavendish measured. On our small scale, the force of gravitation between the Sun and Earth is almost 7 billion times smaller than the force of a third of a grain of salt. One might think that this type of scaling is incorrect since the distance between our mini-Sun and Earth is based on the diameter of the Sun and not a straight scaling of the values. You can see here that this is not true since a straight scaling of the size of each mass as well as the distance results in the force remaining the same. In other words, using a straight scaling of all values leads to no change in the nominal value of the force that is calculated. The force should decrease as the masses and distance decrease. The absurdity of the straight scaling method becomes more apparent when we compare the results to the actual Sun and Earth scaled from their actual sizes and distance down to our bowling ball and pebble size scale. Here we see the results of straight scaling versus scaling that holds all the ratios constant. Straight scaling leads to the absurd result where the force remains constant while the distance becomes increasingly out of proportion to the actual ratios given in the heliocentric model. Using straight scaling, we end up with our bowling ball Sun and pebble Earth as close to each other as possible without touching, while the force of gravitation between them remains the same as the full-size masses. On the other hand, holding the ratios constant, including the circumference, volume, and density, results in the correct distance ratio and an ever-decreasing force. It is clear that for comparison purposes, scaling by holding the relevant ratios constant is correct. Since our mini Earth and Sun are magnitudes smaller and magnitudes more distant than Cavendish's balls, this analysis has revealed that the magnitude of the force of gravitation controlling Earth's orbit around the Sun can be thought of as equivalent to a tiny fraction of the weight of a third of a grain of salt. Standing here on Earth in my backyard, the idea that any control could be manifested between two such objects seems like fantasy or magic. Newton seemed to have some of the same reservations and skepticism about his own law, writing in a letter to contemporary Richard Bentley, the master of Trinity College in Cambridge, Newton's alma mater, that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into it. Gravity must be caused by an agent acting constantly according to certain laws, but whether this agent be material or immaterial is a question I have left to the consideration of my readers. As far as I am aware, no similar experiment at an appreciably greater distance, such as in our scaled-down Sun and Earth, has been conducted to measure the force of gravitation. In our scaled-down version and based on Cavendish's results, are we to believe that a force equivalent to almost 7 billion times less than the weight of a third of a grain of salt can work across 77 feet to direct the motion of our mini Earth? Or even that we would be able to detect its force? Are we to believe that with a force that is a 7 billionth share of a trillion of a trillion of a trillionth of a refrigerator magnet, we could control the orbit of our mini Earth around our bowling ball Sun? Obviously, Cavendish's experiments were conducted under very specific circumstances and conditions, and all measurements of the same sense have been done on a similar setup and scale. In addition to not experimentally establishing that mass attracts mass, Cavendish also did not support with experimentation his assertion that the force he measured was the constant that Newton hypothesized, nor that the force adhered to the inverse square law at all. These conclusions came along with his acceptance of Newton's law of gravitation. Regardless of the reservations of Newton or anyone else, Cavendish and the rest of mainstream science built upon his foundational principles. Let's take a look at how Cavendish accomplished his stated goal of measuring the density and how that value has been integrated into the foundation of the heliocentric cosmology and extrapolated throughout the model. At a very high level, Cavendish calculated a density value for the Earth by taking the force he measured in his experiment, which was of course between two known masses, and comparing it with the force of the small ball when it fell to Earth. The mass of the Earth was then calculated to be n times more massive than the large mass in his experiment. The density was derived by dividing the mass of the Earth by the previously calculated volume of the Earth. Up until Cavendish's measurements were accepted as an accurate value for the density of the Earth, only rough estimates based on an analysis of Earth's upper crust were possible. Cavendish provided a nominal value. The density of the Earth, combined with the fact that the surface of the Earth is significantly less dense than Cavendish's value, led to the conclusion that the Earth's core must be made of a far denser substance than the surface. And although Cavendish himself didn't express his result in terms of Newton's gravitational constant, he did provide the necessary piece of the puzzle to calculate a value for big G. Combining Cavendish's density value with the calculated radius of the Earth provided a value for the mass of the Earth, a value that would be impossible to physically measure. By providing the mass of the Earth with other hypothesized values, it allowed nominal values to be assigned for the masses of planets, their moons, and the Sun. In other words, Cavendish's value, based on Newton's presupposition that the Earth's mass is directly responsible for the acceleration of mass to the Earth's surface, bridged the known with the unknowable. measured with the postulated empirical data with hypotheses. Connecting these two lent credibility to the law of gravitation and allowed the hypothetical explanations for what man has observed in the sky since our dawn to be cloaked in observable truths. Newton and Cavendish turned the weight of a falling apple into the standard model for the cosmos. But is it true? Just because a hypothesis is tied to an empirical standard, does it make it credible? Let's take a look at another case where experimental science is extrapolated into the hypothetical. This is an electropsychometer, or e-meter for short. It was invented in the late 1800s and patented in 1954 by L. Ron Hubbard, the father of Scientology. An e-meter measures the changing electrical charges observed on the surface of the skin. This is a measurable empirical phenomena that anyone with the right equipment could measure. However, Scientologists assert that when they are observed during a process they call auditing, they can identify negative emotional connections from a subject's current or past lives.
Continue through the incident.
Okay, I'm in the ambulance. I can feel it moving. I hear the siren. These guys are talking. And then I
thought I told you.
I don't know, one of them asks the other one. He says, why are you going to drop that girlfriend? And the other one says, well, you know, life is short and...
You want to get stuck in a long-term relationship and regret it later.
Life is short. That's what I said to my girlfriend when I broke up with her. But that wasn't me. I didn't want to break up with my girlfriend. And the stress is killing me. That's something that I always say, but that was those two guys in the ambulance.
This is the end of the auditing session. The pre-clear is bright, cheerful, and the engram has erased.
Changing of the electrical charges on the surface of the skin, much like the effects of items falling to the earth that Newton quantified, is observable, repeatable science. Where the e-meter diverges from empirical science is when Scientologists assert that these changes are tied to negative emotional experiences. Although it is an imperfect analogy, it is a similar leap in logic that assigned the force Newton described with F equals ma to the mass of the Earth and integrated it into his hypothetical law of gravitation. Just as the electrical charges on the skin have not been experimentally and scientifically proven to be caused by the emotional distress from past lives, the forces involved in an apple falling to Earth have not been experimentally proven to be caused by the attraction of its mass to the mass of the Earth. Nevertheless, the proponents of each hypothesis operate as if each is infallible fact, and the values assigned are integrated into the foundations of their respective ideologies. It is this act of accepting unsupported hypotheses and building a science around it that causes both to diverge from experimental science and enter the realm of pseudoscience. Before I conclude, let me restate my points related to Cavendish. First, in strict cause and effect terms, attraction to Earth's mass has not been scientifically determined to be the cause of an object's weight or the acceleration with which it falls to Earth. Neither F equals ma nor Newton's law of gravitation are required to quantify, explain, or describe the forces involved. 2. Cavendish did not experimentally establish that the cause of the force he measured was due to the attraction between masses. Newton's law of gravitation was assumed. 3. The force Cavendish purported to measure, mass attracting mass, is not a phenomena observed on Earth. Unlike weight and the acceleration of falling objects, no one experiences this supposed effect. Assumptions about the causes of the relationships and movements of the celestial bodies, unknowable and unmeasurable qualities, must be brought into the discussion in order for an observation to be asserted. 4. The Cavendish setup is notoriously sensitive. Coupled with the fact that no independent variable is manipulated to explain the entirety of the movements measured, the conclusion he draws are plausible but not experimentally supported. 5. The magnitude of the force that Cavendish measured is minuscule in comparison to the effects attributed to the forces it is said to measure and doesn't support the conclusions drawn. Cavendish assumed that the force he measured would scale from the balls in his shed to the heavens in the manner that Newton hypothesized. The results he reported on the scale he worked were admittedly assumed to hold true for the sizes and distances assigned to the celestial bodies. And 6. Cavendish's measurements didn't substantiate an inverse square quality to the force he measured. His measurements were performed under very limited sizes and distances, yet the derived values were used within the law of gravitation as if those distance and size relationships had been experimentally proven. which they had not. So, if I walked up to you and told you that I had weighed the earth by measuring 1/3 of a grain of salt, would you believe me, or would you call me crazy? If I told you that I had determined the reason for the movements of the heavens by observing some lead balls in my shed, would you adopt my worldview? What if I rephrased it and said that I had measured the attraction of masses and determined the force between them based on the great Isaac Newton's formulas and have determined a value for the gravitational constant? A little more palatable, right? Especially if we already accept the same model of the universe and my measurements support it. What if I wrapped my grain of salt-sized force in complicated calculations and it was broadcast by the schools, governments, and the world's foremost respected scientific institutions as fact? That'd probably make it pretty easy for Dick and Jane Citizen to accept. What about you? Which phrasing do you think more closely resembles the events? Did Cavendish really weigh the earth? In conclusion, we are once again presented with supporting evidence for the heliocentric model that, while plausible, isn't experimentally sound. We have fact mixed with supposition supported by leaps of logic and gigantic leaps in magnitude. Although his measurements have been repeated, Cavendish's conclusions have never been validated. No physical measurement of the Earth's density or mass is possible. In fact, no one has even dug deeper than 8 miles into the Earth in order to catalog its density. Perhaps the best evidence for the fundamental fallibility of Newton and Cavendish's conclusions is the fact that since their time, the descriptions of the forces of gravitation have morphed and expanded to include everything from the contraction of space and time itself, the inclusion of matter and energy that cannot be observed, and even postulates that time travel is possible. This quote by Mark Kasevich, a Stanford physicist that conducted a Cavendish-like experiment to measure big G using atom interferometry in 2007, may sum up the situation best. Either something is wrong with the experiments or there is a flaw in our understanding of gravity. Further work is required to clarify the situation. And while this quote is taken out of context, it demonstrates the uncertainty surrounding the core idea, the very force that holds the entire mainstream model of the world together.
We can measure it, predict with it, but when you start asking, like, what it is, I don't know.
Strict adherence to heliocentrism's theoretical cosmology will insist all of these questions have logical and accepted explanations. They will even go as far as to insist that the problem lies with your inability to understand the answers.
Pay no attention to that man behind the curtain.
The question you have to answer for yourself is, do you want to accept these plausible explanations and the leaps of logic they support? Or do you need empirical, logical, and experimentally validated information to base your worldview on? It's your choice.